everyone, hello everybody. So today we have the pleasure of hosting Daan, who will be presenting his talk on solving problems with unreached basis and other complex set. So he is here for 2 days. He is visiting George Meyerhofer and also Katerina, I guess. So the floor is yours.
Thank you. And thank you for the invitation. It's really a pleasure to be here. It's such a big group. I thought we were a big group in applied mathematics at the Numa section at K-level, but we're twice as big. Interesting people together. I'm really happy to be here. I will talk about some of the topics that have interested me in the past couple of years. I try to keep my talks fairly light, but some of my papers are technical, so if you prefer that, please read the paper. I'll be mentioning them. A lot of what I'm talking about is joint work with many people. Two of them are here, Jörg Meyerhofer and Emil Payen. I'll touch on the connection with the topic of my talk. For the number of that I'll be referencing with Ben Adcock at Simon Fraser University, master's PhD students currently in Leuven, and then many other spots also includes earlier PhD students in Leuven. And the last part of the talk is going to work with Nick Javetten, who spent a sabbatical with us in Leuven last year in the spring of 2022. So I termed the title Enriched Bases and Overcomplete Sets. And so I'll start by setting the stage of what that is about. It's really a topic in approximation theory, really basic. So I'm assuming many of you here encounter problems in which a solution is a continuous function, and you want to represent that somehow as a linear combination of basis functions. And I'd like to contrast 2 points of views here. So the typical way to proceed is to choose a basis of a certain space that's relevant, and to remind you, a basis is complete in some space, but it's not redundant. By far, in finite element worlds, the most popular choice would be piecewise polynomials. And continuing that point of view, you're aiming to find those coefficients, typically by solving a linear system. And in an ideal world, that system would be square, and it would be well conditioned, and that just rarely ever happens. In contrast, if as a solution of a problem you're solving, chances are you've been solving that problem before. You have quite a lot of knowledge of what to expect, and you would like to maybe include that in your approximation space, which isn't an easy thing to do. So I think of certain features of that. Maybe you know it's singular at some places, it has discontinuities. Maybe it oscillates and you know something about the phase, maybe from asymptotic analysis. Maybe you have some numerical data samples. How do you shoehorn that into a basis? They're difficult to do because of these stringent requirements. That's the complete and non-redundant. If you add something, it ceases to be a basis. If it is redundant, then the system you're going to be solving ends up being ill-conditioned. Okay, so I'm going to give that quite a lot of attention. How much of a problem is that? There are methods out there where people go really creative and use what I like to call non-standard basis, and then I generally use that word for anything that's not radial basis functions, fundamental solutions, green functions, reduced order models. Maybe you don't think of this as an approximation thing. Somewhere it is. So can we say something about robustness and accuracy of such schemes? That's been a big topic for me. And here's a simple example of the ideal world where everything is just almost perfect and you understand everything. If you want to approximate a smooth function on a bounded interval, -1, 1, it's a good idea to use Chebyshev polynomials. Of course, the basis of the Chepfun software system, which has been developing the past 2 decades with this group. Another question is what kind of data of the function you're interested in do you need to compute the approximation? And in this particular case, it's a good idea to use Chebyshev roots of an polynomial. And then the system behind this, you don't actually think of this as a system you're solving usually because you can compute the approximation with a cosine transform. You think of it as a transform, but there is a linear system that you're solving. Ax is b, in which a is square, it's orthogonal, so it's well conditioned. Okay, you get something that's close to best polynomial approximation. This is the ideal. That's just the approximation problem. We're not solving degrees or polynomials yet. But if you take away one of the aspects, then things become difficult. The function is not smooth, then the polynomial will actually convert it quickly. If you're working on anything but a bounded interval, there's not a lot of orthogonal basis out there, and it becomes more difficult to see where to sample your function. So you very quickly deviate from this. In contrast, say we have some non-smooth function, and again, this is a simple example. Say I want to approximate some function, and I happen to know that it has a logarithmic singularity at one of the endpoints. So we know that it can be written as some smooth function times the log of x plus 1 plus another smooth function. I just don't know u and v. I know that an expansion is. So a basic observation is if I make an approximation space consisting of polynomials, Chebyshev polynomials again, and I add polynomials times that logarithm, then it's quite clear that there exists some approximation in that space which will represent that function to accuracy. But how do you compute it? Okay, so this is going to be redundant because the set of polynomials already is a basis and I'm adding things. And in fact, this part is also a basis and I'm adding things. So this is redundant by a factor of 2. If you set up a linear system to solve for expansion coefficient, it's going to be ill conditioned. Reason being, redundancy is connected to the fact that there's no unique way to write f as a linear combination. That's what redundancy means. So we automatically have ill conditioning, and we don't know much about where to sample at particular points, let alone solving that system. Okay, so this particular setting, we can actually answer all of these questions, and there's an efficient algorithm which I'll be referencing later, which we call the AZ algorithm, which arose from a number of collaborators that Leuven, Vincent Copé, Matthijs, and PhD students, and Marcus Webb currently at Manchester, also at the time. I won't talk about the algorithm in this talk. I want to talk about the stability, and I'm going to give a fancier example. So this is from a more recent paper, which we call efficient function approximation in enriched approximation spaces, which is available on the setting is quite comparable. So in this example, we're approximating a Green's function of a modified Helmholtz equation. So this is the equation, delta plus E. E plays the role of an energy in the application. The Helmholtz equation would be delta plus k squared. So E is like k squared, but then there's a variation in the vertical direction. So there's a weight, space-dependent weight. So this is something I took from a paper by Alex Barnett and collaborators, which describes propagation of waves in linearly stratified medium. So that paper by Barnett is about computing the Green's function. So we don't know the Green's function analytically, so they have a numerical way of evaluating. But you do know analytically that it has this form, which is not unlike the one on the previous slide. So you know that there exists some smooth functions A and B, and that, like most Green's functions in 2D problems, it has a logarithmic singularity along the diagonal. So it makes sense if you use polynomials that will capture this part, and you add polynomials times a logarithm, that there must exist some good approximation of that function. But how do you compute it? And this is just a figure taken from the paper to show that it can be done. On the right, you see errors ranging between 10 to the minus 6 and 10 to the minus 10. So in this case, I use bivariate polynomials and bivariate polynomials times that logarithm on the diagonal. You do see slightly larger errors on the diagonal, which makes sense because the function is unbounded there. But I want to focus on the figure on the left. So the squares here would be the polynomial approximation of that function, which of course converges very slowly because of the singularity. And then the circles are convergence of our numerical method using these enriched approximations. So it works very well, but it works so well that it actually goes down here to 10 to the minus 10 accuracy in 2. And I think that deserves some explanation. Because the number of degrees of freedom we're using here is 10,000, and the numerical method actually is a least squares problem. We're solving a rectangular system, which should be like 20,000 by 10,000. It's extremely ill conditioned, and yet it seems to be very numerical. Okay? So can we explain that, and what's behind that? Can we use it in other applications? The algorithm actually solves that in a fraction of a second, but I'll refer you to the paper. This is just a figure from that paper by Alex Barnett to show what the Green's function looks like. It's oscillatory, as you would expect for a wave propagation problem. And we chose this not just because of the diagonal singularity, but because the oscillations mean that it's not that trivial to approximate those functions. We kind of need high polynomial degree. We actually need large number of degrees of freedom, and so we need a method that's stable and robust. Okay, so that's one way you could add things to a basis if you know a singularity. Another way you arrive at redundancy, which has been a theme in my group before for a long time, is if you want to approximate a function of some irregular domain. In this case, the irregular domain is my home country, Belgium, and we took data from NASA on the left and from the European agency on the right. This is Belgium and the Netherlands, and the data represents the height of the country. Okay, so as you see here, the Netherlands is dangerously close to sea level. But I'm interested in an approximation problem, and here I'm approximating the height of Belgium using the Fourier series. And a trick to do that is to put the irregular domain inside the bigger box, using a classical temporal product Fourier series on a bounding box, and using that to approximate the function on that irregular. This is something that appears in a lot of something called embedding methods, or called inverse boundary methods. Is quite popular in computational fluid dynamics. It's based on similar ideas. The point I want to make is if you start from a basis on a domain and you use that to represent a function on a subset, then you get something that's redundant, and you can expect condition systems try to fit the representation. Okay, how can we explain this, and what do we learn from that? So the way I see things now, there are two aspects. On the one hand, we have the approximation space. You have the 5 Ks that you've chosen based on what you know about the function, the solution of your problem. And on the other hand, there's the problem of what kind of data do you need from a function in order to actually be able to compute the approximation. Okay? If you use that, you sample in a bunch of points, n, which could be different from the number of degrees of freedom. You arrive at a linear system. It might be unconditioned. And what we analyze is if you solve that system using truncated SVD with some threshold epsilon. So this is a regularization scheme to solve the conditions. And apart from that, there's no assumption. It doesn't have to be a basis. I'm just assuming it lives in some Hilbert space. For all I know, there could be duplicates. I mean, it could be so redundant that you could have 1, 1, x, x, whatever. So no restrictions yet. And there's a generic error bound, which Benato and myself derived, which looks like this. So this is the approximation error measured in that Hilbert space, which we assume exists. And then on the right-hand side, there are 3 terms. 2 of them relate to approximation error. So the truncated SVD regularization is solving some optimization problem. It optimizes over all possible coefficient vectors, and it balances these 3 terms. So the first 2 relate to how well these coefficients, if you use them as an expansion in the representation, how well it actually approximates f at a continuous level and at a discrete level. And I'm kind of assuming that you've chosen 5 precisely because you know f is well approximate. Yeah, that was the whole point of the setting. The unexpected thing, or maybe the thing to be looking after, is this 3rd term, which is the coefficient norm, the norm of those expansion coefficients. What does that tell us? It tells us if there exists a good approximation in that space, these 2 terms are going to be small. But if the coefficients in the representation are large, that will affect your accuracy. That's a relevant conclusion, and this is really a numerical aspect. This is the first 2 are approximation space, and this thing, the size of the coefficient, actually ties the representation that you've chosen to your error. Okay.
So here Z is a set of all ZK, all ZK, and okay,
Yes.
and
You're optimizing over all.
and it's not a phi n, it's maybe a phi k, I guess. Yeah, and
So
and B and excuse me, and B is the data that you have in point 2.
Point samples
Yeah.
or inner products.
Okay,
For a
okay.
given approximation space, eventually your estimates is highly dependent on the system that you use, right? I mean, suppose you had the same approximation space but a different system fitted decay, that you massage them in a way, maybe, I don't know, but
Yeah.
would you get a different estimate in the end? I mean,
You get a different bound. Yeah. So for example, if you orthogonalize,
that's a stupid,
Then there is a-
stupid. Yeah.
well, if you orthogonalize, then there's a connection between the size of the function and the norm of the coefficients, and these terms can be far. Of course, orthogonalization is expensive, but it would still apply, but the error bound would be better. Okay. So what have you learned so far? You're going to find an accurate approximation if an accurate approximation exists and with bounded coefficients. So there's no impact of the condition on it. So the fact that the system is unconditional or even singular doesn't matter. The thing is that you want to have a representation with bounded coefficients. Okay, 2 more things. There are some constants here, kappa and lambda. They depend in a very complicated way on how we've chosen the samples, but there's kind of a simple procedure to make sure that they're of 1 and that you can forget about them. Final aspect, there's an epsilon here, which was a regularization threshold, which you can choose to be like 10 to the minus 12. So if there is an approximation with epsilon accuracy and with reasonable size of coefficients, this error actually predicts that you're going to get O of epsilon error, and that's pretty much what you see here. In our experience, if you use backslash in MATLAB, it kind of uses 10 to the minus 12 as a regularization threshold. Okay, so there's a possibility of having O of epsilon error in spite of solving very ill-conditioned problems. Okay, and then we wonder, and this is in two papers we've been at, what kind of conditions do you actually need, or what kind of conditions are sufficient such that this error bound actually is small for all the functions in space? And then we identified two, one of them connected to the space and one to the samples. I like the expressions because they're so short, they don't convey a lot of intuitions if you haven't seen expressions like that before. So I won't go into the technical details of that, but this is really a concise way of putting it. So about the space, sorry, the next best thing beyond the basis I like to think of is a frame. So a frame is a set of elements such that these two inequalities. That condition is going to ensure that for any function f in your space, there is some representation that is accurate and that has small norm approximations. Okay, so the frame condition ensures that these two terms, the first two can be small, while the third one is O of 1 at the same time. Okay, so if you're working with a frame, there's hope of getting O of epsilon accuracy for any function in your space. Second has to do with the discretization, and the condition is structurally similar. It's a pair of inequalities, and we use the terminology of sampling. We call this more Sigmund inequality. It kind of looks like a norm equivalence. So the main message here is that if you choose the number of data points to be much bigger than n, it's very easy to satisfy this equation. So this is the reason for abandoning square systems and looking at rectangular systems or these square systems, such that the norm of continuous function is equivalent to the discrete norm of that. Okay. If you're working in L2, then this is going to be an integral. And this is like a Riemann sum. So it's sufficient to take sufficiently many points spread over your domain. Importantly, take more points than n, and this is going to be fine. And then what we can show, if you do that, is that lambda and kappa tend to constants. So in the limit of large over sampling, these constants are going to be fine. And if you have a frame, these two terms are going to be small, and this one's going to be 4. Okay, that's a theoretical setup. I've looked at a number of applications in which ill-conditioned systems arise, and then the first question people have to reading is, am I using a frame? And then the answer usually is no. So it's not essential to be using a frame. It's a sufficient condition. If you're not using a frame, though, you've cooked up a number of special basis functions based on what you know of f. So together in a big least squares problem, if it's not a frame, it might work well for some cases. But there are always going to be cases where it fits, in the sense that there's going to be functions which don't have a. If these functions will arise in practice because they're unphysical, then that's not an issue at all. Okay, what does that mean in practice? Solving a linear approximation problem. My first recommendation, if you hit ill conditioning, or if you're unsure of whether the set of functions is a basis, or you don't know what the space is, it's safer to do these squares. Sample lots of points. Okay. That removes the difference between continuous and discretization. If your system is ill-conditioned, use truncated SVD among all regularization techniques in a certain sense. And then the second major thing is, you should just be concerned with the approximation error, but also monitor the size of the coefficients. If the coefficients are getting large, you're going to lose accuracy. And you think about what happens, what can you add to this set of functions to represent f with smaller coefficients? It will improve your effect. So by and large, if you oversample enough, the error is going to be dictated by this simple quantity, approximation error plus coefficient. So if you think about this part, this is just the best approximation. Okay, so if you study best approximation for your spaces, that's good. Now look at coefficient norms as well. And if they're bounded, then don't worry about your conditioning. You can solve the system dynamics. Okay, I want to highlight one of your papers actually, because I think it's underappreciated. So if you wonder how to sample a function in a funny function space and how to choose the squares one, there's a very generic procedure to do so, which is entirely constructive, might be a bit expensive. Made by Aldea and Giovanni Virati. Optimal weighted least squares methods. There's a sequence of papers, more recent ones with Mathieu as well. It assumes you have an optimal basis that may require a computation. Explicitly computes something called Aristotle function, and that defines density for which you can sample randomly. Okay? Ever since I learned about this, I've been using it over and over again. It's like a hammer, which you can hit a lot. Okay, that was part one. Hope you remember, if you cooked up a funny approximation space, consider discretizing to a rectangular system and watch the norm of the solution of this system. I want to touch on two applications which I've explored in collaboration with people here. So with Björk, we looked during his PhD at boundary element methods, integral equation methods in scattering problems, and there are different ways of discretizing integral equations. The two predominant ones are Galerkin and provocation. And the Galerkin discretization in the field is known to be robust. There's a lot of analysis. It actually converges quicker than collocation-based systems, but it's expensive. We're in the setting of integral equations. There's one integration coming from an integral operator, and there's another integration coming from the projection of the fact that we do today. This is a Green's function, which can be singular. So for 3D problems, you're solving, you have to evaluate a lot of four-dimensional, singular or nearly singular integrals. This has been a major topic in the Ben community for decades. Collocation is a lot easier. You don't do the projection, so you have just one integration associated with the integral operator. But now the question is, how do you choose the collocation points? And then that problem is comparable to the choice of interpolation. So it's not trivial, and it's known to be less robust and sensitive to how you choose the collocation points. And then the simple change we applied is to allow more collocation points then to look at a collocation scheme in an oversample sense, in a least squares sense, and to see what happens. So it's a very simple change. If you already implemented collocation, just add a few extra points. So there's no ill conditioning here. There's no redundancy. Everything is base. Everything is just fine. So this focuses on discretization. I've taken one figure from our first paper on this topic. So there's a scattering problem we're solving on a 2D domain shaped like a kite, and we're solving an integral equation on the boundary of the kite, and then later on evaluating the solution of the Helmholtz equation at this point here. And then we had to dig quite deep into the literature to isolate criterion that tells you the convergence rate at that. And when I say we, I mean did that. So using piecewise linears on the boundary of that domain for the two bases, you actually get fifth order convergence at that point. It's twice the order of your bases plus one. That's Galerkin, that's the black line here. If you use collocation, you only get the order of your bases once plus one, and that's the gray one, third order. So it's third order versus fifth order. If you oversample, this curve goes down substantially, maybe like 2 orders of magnitude. So linear oversampling, you improve accuracy by fixed amounts. We were surprised to find that if you oversample way more heavily than that, if you oversample quadratically, which you would never do in practice because that would be very expensive. If you oversample quadratically, then you actually get a faster convergence rate than the Galerkins. Actually get 6th order convergence in this case for reasons having to do with duality arguments and solid spaces, in which ranges of solid spaces in which the solution of the integral equation is. Okay, so a fairly simple change improves your accuracy of the collocation scheme quite a lot, makes it more robust. We have other examples of domains with corners in which collocations sometimes fail, but then with some oversampling, with at least convergence. That was a nice result. Collaboration with Emil, again, a scattering problem, but now solving a PDE, the Helmholtz equation. And we were interested in Huybrechs methods. So Huybrechs methods is a class of methods which is notorious for giving rise to very ill-conditioned linear systems. So what you do is you try to solve a PDE by using basis functions which actually satisfy the PDE, in this case, plane waves. The wave number, any plane wave where D is an angle. Plane waves in any direction would satisfy the Helmholtz equation. And you just have to pick a boundary condition. So that's an ill-conditioned problem. And then people observe that this works in a lot of cases. Very often with the number of degrees of freedom that's smaller compared to piecewise. But there's a recurring question in the field, like which set of angles should you choose? What is a good selection of plane waves? There was a lot of great analysis, best approximations in those spaces by Marcus Melenk, Andrea Maiola, Ralph Hittmeyer. You can represent solutions to the Helmholtz equation using plane waves with exponential accuracy. Okay, that's a known result. The first thing we proved is this is true. You can represent solutions to the Helmholtz equation using plane waves with exponential accuracy, but the norm of the coefficient is unbound. Okay, so even though good approximations exist, they are numerically not computable. And once you know that, you can find problems for which these methods. And now we hit a major obstacle, because I like to look at different fields in which people have creative spaces, and I can analyze and diagnose a problem saying it's not a frame, but then what? How do you fix that? There's no constructive way of doing that. So these have been done the work of Emil to add additional functions so that you can control the size of the coefficients. Okay, so this became quite complicated. What we did in this particular case is to allow the angles to be continuous. Then Emil found a transform associated with that, which was unbounded on the real line, but bounded in the complex plane. So that sort of tells us we need to consider complex angles, which doesn't make sense physically perhaps, but formally this is still a plane wave which satisfies the Helmholtz equation. And choosing complex values here means that the plane wave will decay exponentially in one direction. And these are called evanescent waves. Hence the title of the paper, Stable Approximation of Helmholtz Solutions by Evanescent Plane. So at the continuous level, we have a transport, continuous angle test. We also happen to have an orthonormal basis. And so we could use the hammer to sample angles, in this case, to come up with a suitable set of plane waves to use to solve. Okay, the main point I wanted to make is, we know this is small, but we really want to get a handle on the coefficient form. And so again, I took one figure from that paper. Our analysis was on this in 2D. So this is a Helmholtz solution, non-trivial. This is what you get using just plane waves. And importantly, the scale here is order 1. So the error is order 1. It's not a frame. You can always find a problem with the method pairs. And the thing I want to point out, if you use these complex angles as well, you use a set of plane waves and evanescent waves, you can go down to 10 to the minus 12. This range between 10 to the minus 12 and 10 to the minus 2. So again, you see rock solid stability if you combine good approximations with bounded coefficients, regardless of how the condition the system is used. So, okay, if you think of other approximation spaces, please talk to me after the talk. I want to spend a bit of time now talking about a more recent interest, and this connects to Nick Jafetin's visit. We talked a lot about rational functions. So he's been involved in Chefron for a long time. The more recent passion is rational functions, and we understand much less about rational function approximation than polynomial approximation. And there is a connection to the earlier part of the talk. But a problem that has fascinated me for a while now is a very canonical model problem when approximating functions with singularities, and that's the approximation of the absolute value of x on minus 1, 1. So this goes back over 100 years. The Poussin, who was 11 at the time, constructed a polynomial approximation of abs of x that converges very slowly, like 1 over n. And then he asked, can you do better? And Bernstein then proved in 1912 that that's the best you could do. And the reason they were interested was at the time they knew if you understand polynomial approximation of this function, we essentially know approximation of functions like ck. And that's exactly how it happened. This is how we developed this link between smoothness of a function and convergence of polynomial approximation. A link that underlies a lot of concepts in numerical analysis, everything based on. Okay, of course, polynomial approximation is very slow. To mention the approximation of square root x on 0, 1 is equivalent, both for polynomial and rational approximations. You can convert smoothly the one problem into the other. So polynomials have a hard time dealing with singularities. If the polynomial expansion converges in a complex plane, as soon as it hits a singularity, convergence stops. Rational functions do not have that problem. It's surprising result at the time, I've been told, wasn't born yet. In 1964, he showed that rational approximations to the square root of x, 0, 1, exist with good exponential convergence in the degree of the approximation. So rational functions have no problem dealing with branch points or even branch cuts. The rational function will put poles on the in the complex plane. Rational approximations can converge beyond singularities. Very different component. Okay. Short time later, Van der Voorde and Scherer, and then Babushka and a number of collaborators in a series of papers started investigating HP type approximations. So HP mesh refine, in which you don't just refine H, but you also allow P, the polynomial degree, on your mesh element. And then this was a model problem that they studied because it's amenable to analysis. And they also showed that you can get root exponential convergence to square root of x of such approximations. In fact, it's really really precise, leads to the optimality of geometric progression, metric one with a certain package. Okay, connecting to the topic of this talk, piecewise polynomials is very much associated with the notion of a basis, and rational functions, at least the way we compute them numerically these days, is much closer to that notion of least squares fitting by solving no conditions systems. But the fact that they need to the same convergence rate is not a coincidence. And in fact, there's a very close link between rational functions and piecewise polynomial approximation. A link that was known People would maybe not appreciate it very widely. There was a paper about that with Nick connecting this with some other functions. Okay, so another paper with Nick and a student of mine is about rational approximation to square root of x. And we wanted to find a numerical scheme to approximate this function, again, as a canonical simple model problem. It's known by Huybrechs in the 90s that the best rational approximation in a max norm scales at a certain rate, either minus pi squared of 2n, so good exponential, but he knew the factor, and in fact, he actually knew the constant, so it's short bounds. And a numerical construction that we come up with satisfies a similar bound with a factor of 20 rather than 8, so it's within a factor of 3 of the best we could do. And it's essentially a least squares fit with an enriched basis. So we have polynomials, to 0, 1. And then we add rational functions in partial fractions form. So I told you that representation is important. So pk's would be poles of this function. We multiply by pk so that these functions are normalized on 0, 1. They don't go. This has to do with the upper inequality of the frame. Normalization establishes a number. We choose the poles a priori, and we choose them to be exponentially clustered in a way which Nick calls tapered exponentially clustered. So it's geometrically graded, but slightly slower than that according to this formula. And then we work hard to get like the best values. And so we end up solving in these square space of polynomials with rational functions added in barycentric in partial fractions form. And so here the black line is the minimax, the best rational approximation, highly nonlinear problem, non-trivial to solve. And then the purple line is our construction, which converges at the same rate, slightly higher. And as there are examples before, all the way down to 10 to the minus 12. Okay, this is a canonical problem. Nick uses that in the class of methods he calls the lightning solvers, where you cluster poles of rational functions close to points where you expect a solution of the Laplace equation to have a singularity. Okay, so nonlinear problem, this is linear. So you fix the poles of the rational function, it's just about fitting the coefficients, that's a linear. Okay, this was a surprising observation. At one point we sat down and we tried to visualize these bases. So we know partial fractions from early calculus to convert the rational function into partial fractions form, and it helps to evaluate. So this is a plot of those partial fractions, 1 over x minus pk, where the pk's are exponentially clustered, and you look at them on a logarithmic scale, and then it just looks like this. Okay, so rational functions don't have compact support, and non-zero everywhere. But if you look at it in this way, it's very clear that all of them have sort of an active window. In fact, they resemble what's called activation functions in neural networks. By the way, if you use a rational function as an activation function, the composition of rational functions is rational. So this is geometric mesh requirements. This is a visualization of rational functions doing exactly what you do in H requirements. Okay, except that there's no P here. To be complete, in HP requirement, the optimal scaling is to have your P, your polynomial degree, increase a little bit away from the singularity. There's no P here. The alternative is that as you geometrically refine, it becomes slightly sparse, so slightly slower than exponentially, or slightly faster. Okay, so it was the last day of Nick's visit in Leuven. We made this plot and suddenly our eyes were okay. Final topic, HP's type adaptive measures. Of course, we use constantly 2 and 3D. The rational functions of one variable are like HP requirement. What about rational functions of several variables? I'm convinced that there remain a lot of links. We just don't have good numerical tools to manipulate multivariate rational functions. So we have an ongoing project with Jacques-Louis and my student, Nicolas, currently in Cambridge, and where univariate rational functions can approximate functions with the branch point singularity. This is what I've shown you. If you use multivariate rational functions, you can approximate functions with curves. For example, the kind of edge singularities that you would get in a 3D PDE problem. Actually, we haven't done that yet. I'm going to show you an example. This is the same Green's function that I had before of this modified Helmholtz equation, which has a singularity along the diagonal. And now I'm making a multivariate rational approximation. And the approximation space that we're making is a polynomial part. E of x and y is a polynomial in x and y. and I'm going to have a rational part, not partial fraction, but it's like 1 over x minus y. So it has poles along x equals to y, but then with a small shift. And we have a residue which we also allow to vary in space. So qk would be a pole. And we take our shift to be complex, and then we do a big least square fit. We choose sufficiently many sample points, we cluster them similar to the way we cluster the poles. So these imaginary shifts are plus or minus 5 times pk, where pk are the same as for the square root of x. Okay, so what I'm looking at in the left, this is a bivariate rational function with like curves in the complex plane on lines parallel to the diagonal, which are able to represent this function very well, to like 5 or 6 digits. Accuracy by solving a big discrete least squares problem. We're exploring other cases. We could do algebraic curves, elliptic curves, because they have an algebraic polynomial expression. So that the game to play is to put that polynomial in the denominator at a complex shift, cluster them exponentially, and just do a big least squares fit. And hopefully the paper will be ready in the moment. And I think I'll stop here. That's all more material. Thank you for your attention. Thanks again.
Thank you. Thank you, Dan, for this very nice presentation. So are there questions, comments?
So is it fair to say that this method is adapted to the situation where you know in advance the location of the singularities? And what if you don't really know where they are, and just from out of your data you would like to essentially reconstruct? Maybe this is a different situation.
Yes, absolutely. It's a very fair thing to say. So you can only linearize the problem if you know exactly where the singularity is, or a point in 1D or this curve in 2D. And so you sort of lose the nonlinear approximation power of rational functions. In 1D, I really want to mention the AAA algorithm. So for univariate rational approximation, AAA will actually adaptively find singularities, and it does so very efficiently and in a very seemingly stable way. So just applying AAA to square root of x on 0 to 1 without giving it any more information will cluster poles exponentially to 0. So the dream is to develop a bivariate version of AAA to actually do nonlinear approximations.
By the way, this bivariate things looks more like a univariate thing, because it looks like a ridge. I mean, it looks like constant in one. It looks just a function of x minus y, so a univariate function. So I don't know.
We'll play with the parameters. So the function we're approximating is like this one. There's actually variance, but it depends on how you choose the parameters. Okay, I'll try to make it more challenging before because there's an open problem though. So if you know the location of singularity, then you know what to put in the denominator. But the residues, they should vary along the tangential direction, along the curve. And it's not clear in general what a good basis is for that. So in the particular case of the diagonal x minus y, we know that k can just be a polynomial of x plus y. Okay, but for general curves, we don't know yet what to put in the numerator.
Okay. So there is a question on the line. So Fatma, can you open your microphone and ask a question if you wish?
Good afternoon, and thank you for this nice talk, actually. I just want to know whether, actually I didn't start from the beginning because there is a difference of power from Algeria here, whether or not to use radial basis functions and also orthogonal polynomials like Legendre and Huybrechs.
So the question is whether we use radial basis functions and orthogonal polynomials. So
yes, like the spectral methods for this issue, actually.
So in this case, to represent this polynomial part, we do use a product of orthogonals in the x and y direction. So classical tensor product basis. Radial basis functions are also known for producing ill-conditioned linear systems. And I have a paper on that with Ben Adcock and Cécile Perret analyzing the stability in the case of the Gaussian kernel. So there are different regimes in radial basis functions involving choice of what they call the shape parameter, which determines the width of your kernels. And if you analyze this quantity, then there's an optimal choice of a shape parameter that will balance these things optimally, which sort of makes your Gaussian kernel a shift so it looks like splines. So it makes the conclusion makes perfect sense, but at least we have analysis guaranteeing in this particular regime that you can use a Gaussian kernel without a change of basis and have a numerically stable scheme. I have a follow-up more recent paper with a student teaching Zoo, K11, about efficiently approximating these approximations, again using the Gaussian kernels. And in a 1D setting, it's n log n. So we can compute an approximation to a function with like 10 million Gaussian kernel with some restrictions that should be equispaced. But it's a variant of the AZ algorithm, which I've mentioned but not explained.
Okay, thank you.
Other question?
May I ask one? Okay.
Yes, go ahead.
So for example, you mentioned reduced modeling, like reduced base. So reduced basis is typically something where you generate very good approximation space, but with the generator highly in condition, I mean, very close to linearly dependent as you. So our way to solve this is to do some sort of Gram-Schmidt orthogonalization on the fly. So what would advocate for a different approach where you don't do that and you do this kind of truncated SVD if you want to use them for solving in easy, fast online way? I mean, my understanding is you want to avoid orthogonalization, Gram-Schmidt orthogonalization.
Yeah, actually, I had exactly the same question, but in a general case. What I would do in such overcomplete case, in which actually it's a basis. It's still a basis. Okay, there is no linear combination that is equal to 0 with. Yes, but in the cases that you advocated, there is none. Okay, so what I would do, I would choose n. Okay, I would orthogonalize this function like in the reduced basis, but in the general case, and then it should be stable.
Yeah.
So what is there a link between your approach and such a preliminary orthogonalization?
So that approach is not only stable, it's also more accurate, because if you regularize, you actually throw away a part of the approximation space. So if you orthogonalize, you're going to see faster convergence. Okay, so if that's feasible, that's always better. An orthogonal basis is always better than a frame. Reasons I have for selecting frames is, for example, in this extension framework, you can have an approximation of f as a linear combination of Fourier basis functions. And so a constant coefficient differential operator is going to act diagonally on that function in that representation, but not in the other one. Another thing is realization might be expensive. Okay? If that's a price you can pay, then go for it. And then the third thing that I wonder is if you orthogonalize an ill-conditioned set of functions, I mean the map from the set of functions to your orthogonal basis is itself ill-conditioned. Okay? The ill-conditioning doesn't go away. So if you represent your orthogonal basis in terms of the original representation, that will be unstable. So if you orthogonalize,
but maybe there is this online offline paradigm. Maybe it's good to invest a lot offline to have a very good system. To avoid this.
Yeah.
And then because here I get your point that there is a preservation of problems.
Yeah.
yes.
Okay. But I'm wondering if in some limit, for instance, certainly not what I will say, but if epsilon goes to 0, does this approach, which is still stable for epsilon positive, does this approach is related to an orthonormalization process, depending on which norm you use for the H or which norm you use on the 2. For the norm that you choose on A, you can choose another type of norm. And maybe there is one that will, in some limit, make the two approaches more closer.
Could be. I think that's very much depends on the setting you're in. But I want to point out that, I mean, if you do use a truncated SVD, that's also expensive. And in fact, this is like an orthogonalization. So you're actually spending the effort in orthogonalizing and then throwing away and going back to the original representation. Okay, so this only makes sense if you have an alternative way of, I mean, in comparison to orthogonalizing, if you have an alternative way of solving that system.
Okay.
But I can only observe that there are quite a number of applications in which people choose a 5Ks because of the properties. And then it's interesting to retain them and not having to do a change of basis, which comes with a deprecation cost and also a lot of storage to remember what the representation actually is.
Good.
If you have a basis, space is always better. It's just
Yeah, yeah.
is the next best thing.
Yeah.
That's-
No, but as you said, using an SVD or autonomizing it is already challenging numerically. Okay, so it has a cost. Other questions? No? Okay, thank you again.